Hello, I'm Benjamin Diamond, and I will be presenting many out of many proofs and applications to anonymous Zether. So let me start with a widely known fact, which is that standard issue cryptocurrencies like Bitcoin lack privacy and, of course, don't have formally articulated privacy guarantees. I can point to the sort of regular manifestations of this fact in the media. And concurrently, there are various efforts underway to make cryptocurrencies with better privacy properties. For example, Monero and Zcash, among a number of other efforts, and these have been successful. What I want to argue in this talk is that these currencies have focused largely on making transaction sizes be really small, and they've succeeded in this, bringing the transaction size down to just a couple kilobytes and leading to reasonably sized blocks. But that in focusing so much on transaction size, most efforts in private payment have actually neglected a further factor, which has arguably been more operative in preventing these things from getting used in practice, and that is the feasibility for use with mobile devices. And the reason is that the way these currencies work, in order to run a wallet, you wind up incurring a substantial bandwidth and CPU burden. And the reason why is that in order to even know what funds are yours, or which transactions are to you, you essentially need to scan through every transaction posted to the blockchain. You need to download every block, and moreover, you need to cryptographically process each transaction, which shows up in the blocks. And this issue is not just theoretical, but has practically affected the efforts which have been made to make wallets for these currencies. So into this picture arrives a new protocol described in a recent paper of Benedict Boons, Shashank Agrawal, Mahdi Zamani, and Dan Bonnet called Zether. And Zether is interesting for a number of reasons. But among them is that it essentially solves this bandwidth and CPU issue. And what that means is that my wallet, my phone, can be off or offline for any amount of time. And when I come back online, if I want to say know my account balance, I can learn that just by querying some small constant amount of data. And this is true regardless of how long I was offline for, right? Similarly, if I want to send funds, I can learn all I need to know to do that just by downloading some small constant amount of state from the blockchain. Again, regardless of how long I was offline for. So this is really important. By way of background, I will quickly explain how anonymous Ether works. So the idea is that within your global Ethereum state, of course, anonymous Ether could be a standalone cryptocurrency, but Boons et al. Didn't envisioned it as a contract in Ethereum, and I do the same. So beginning with a pre-existing ERC20 contract, you could use wrapped Ether, or you could just use Ether. But you can deploy a linked anonymous Ether contract with sort of on and off ramps for funds. And the actual private payment happens within the contract. The way this is done is by storing a global table, which takes public keys and maps those to encrypted account balances, where each account balance is encrypted under its own key. And to send funds, the sender should select some subset or ring of this global table, which contains the sender and receiver and also contains some amount of other accounts called decoys. And the sender should encrypt the amounts by which the sender wants to change the balances, right? So for example, -10 for the sender, +10 for the recipient, and of course 0 for the decoys. The sender should then attach a zero-knowledge proof, which asserts that this transaction takes the right form. We'll talk more about this in a bit. And the idea is that if the proof passes, the contract can apply the transfer using the sort of homomorphic property of this encryption scheme, right? You can see that the accounts have been overwritten now with new values where the transfer got effectuated. And the key property is that I, a user, can sort of sit back while this happens arbitrarily many times, and whenever I want to come back and check my account balance, I just look up my own table entry, and I can do that right away regardless of how many times this has happened in the intervening time. So zooming into the zero-knowledge proof, let's talk a bit about what it should show. And intuitively, we want to show that the transaction takes the form here, right? So for example, each element should be a well-formed ciphertext under the right public key. In practice, we use El-Gamal. There should be two among these which encrypt exactly opposite amounts under their keys. Whichever of those is negative, the sender should have authority to spend from that account. And moreover, this transaction shouldn't cause that account to become negative. So that's overdraft protection. And of course, all of the remaining accounts should encrypt 0, right? This is crucial, or otherwise the sender could sort of change around arbitrary bystanders' account balances in the course of the transaction. Okay, so what this paper does is propose a zero-knowledge proof protocol for this idea, which moreover has good asymptotic and concrete performance. Now, the thing to keep in mind with anonymous Zether is that you pay for privacy in a certain sense, right? In the sense that the bigger your anonymity sets get, the better privacy you get, but also performance will degrade in some sense. And then the question is, what is the nature of that relationship? Well, in this paper, the protocol I propose, the proofs grow only logarithmically in the size n of the anonymity set. The prover's runtime grows quasi-linearly, so n log n. The verifier's does too. And the transaction size, of course, is linear because you have to include this array of ciphertexts, but nonetheless has reasonable size in practice. And then finally, we use only standard assumptions and have no trusted setup. Okay, so for the remainder of the talk, I will go into how this actually gets achieved in practice. And the first starting point is a paper of Jens Groth and Markus Kohlweis called One Out of Many Proofs. What this paper does is take a public list of commitments, which both the prover and verifier know. The prover knows an opening of one of these elements to 0. And what the proof shows is knowledge of both of these data points, right? So first the secret index and then the secret randomness. And the key property is that, beyond being sound, is that in the eye of the verifier, the index where this commitment to 0 resides should stay secret. So in this protocol paper, I introduce many out of many proofs, which is a direct generalization of one out of many proofs. And one way to think about how this works is that instead of pointing to a single secret element, the prover can point to a secret subset of a list, where both the contents of that subset and the order are secret, right? So this is actually an ordered subset. And then argue that this ordered subset, whatever it is, satisfies some linear equations. So just pointing to a concrete example, what we show is that after going through this known list in some secret order, that you wind up with a reordered list where linear equations are satisfied, right? So for example, these top two elements should add to 0 and the rest should be 0, right? Of course, this is exactly what we want to show in anonymous Zether. And the key property is that it remains secret to the verifier what that reordering was, which caused these linear equations to get satisfied. In this particular case, that amounts to saying that the indices where the sender and receiver reside should remain secret, which is exactly what we want to show. So how does this work technically? Well, going back to regular one out of many proofs, the way these get done is that the prover chooses and, in some sense, commits to a linear-sized array of polynomials. And the key property of these polynomials has to do with their degrees. So only at the secret index is this polynomial of high degree. It's degree m, where m is log of the length of the list, and monic. And the rest of these are of lower degree. And when the verifier sends a challenge, the prover can convey to the verifier the evaluations of these polynomials at the challenge. First of all, the verifier at this point is sort of convinced that these take the right form, that they're indeed evaluations of polynomials which have the right structure. One is of high degree and the rest are not. And moreover, the prover can convey this information in sort of log n communication, which is a non-obvious fact described in the original paper. And the idea is that if the verifier takes the dot product between this vector of commitments and the vector of scalars, then by construction of the polynomials, the verifier ends up with exactly the desired secret element raised to a high power of x, and then plus sort of lower order terms which depend on lower powers of x. And the prover can anticipate these in advance and sort of send the appropriate correction terms before seeing x. Now, there's a powerful technique here which is being left on the table, which is that at this point, once the verifier has access to this vector of a special form, though the verifier by design knows nothing about which index contains the high degree polynomial, the verifier can nonetheless permute this vector in a predetermined way and get a good idea of what kind of path can be traced through the vector by this element as these permutations are conducted, right? And then redo the dot product each time, roughly speaking, right? So again, for example, we start with a familiar picture, just like in regular one out of many proofs, and take a dot product, wind up with some element. But then we permute this vector. In this example, there is a two-step circular shift permutation, and then do a second dot product. And we end up with something else which is equally not known, but we know how it relates to the first one. It's just down by 2, possibly with a wraparound. And keep doing this and permuting the vector until we've cycled through the whole vector, and what we get is a subset of the original vector of a very specific kind, but whose contents and order are both secret. Plus, of course, lower order terms, which can be canceled out by the prover in a similar way. And what we can then show is that this subset satisfies some linear equations. Either they are all 0 or they reside in some known hyperplane or something like that. And we can see why this is a generalization of regular one out of many proofs, right? So that instance corresponds to the case where the permutation is the sort of identity permutation, so you just get the one element, and then the map is the identity map on one variable, right? To satisfy that map just means to be 0. Okay, so just one point about efficiency in practice is that if you unwind these sort of constructions, what you wind up with is writing down this vector of pi's in the top row of a matrix, and then obtaining the subsequent rows of the matrix by permuting the top row. And in the case that this permutation is a shift permutation, and I argue in the paper that this in some sense is the canonical case, then this matrix is a circulant matrix, and the multiplication, which is now a convolution, can be done in log n time using the number theoretic transform. So this is a way to get really good performance for the prover and verifier. Okay, so this gives you some really nice applications in practice. For example, given any vector of commitments, I can argue that I know how to open those to a standard basis vector, but without telling you which standard basis vector, right? So 1 is 1 and the rest are 0, but you don't know which one is 1. For example, I can show that given the vector of messages after getting shifted by some secret offset would then reside in a hyperplane, but not tell you what that offset is. I can, for example, I can argue that either all of the even indexed commitments I can open to 0 or the odd indexed ones, but not tell you which of those. So these are all sort of much richer statements than you can prove using just regular one out of many proofs. Okay, so I've fully implemented anonymous Zether. You can find the implementation in my GitHub. It's also mirrored in Consensus's GitHub. And you can see that the performance is more or less comparable or competitive to classic standalone private payment cryptocurrencies, even though, on the one hand, this runs entirely within a smart contract, and moreover, obviously has these nice wallet properties. Gas use on the Ethereum network is fairly high, around 7 million, so this might make it prohibitive for use now because of fees. But perhaps when Ethereum 2 comes out, this would be more feasible. In any case, that is my time, so thank you very much for listening.